How do very large deep learning jobs work? In this video, I'm going to tell you about principles and techniques for training very large deep learning models. This means training models with many parameters on datasets that are many terabytes or even petabytes large, using many GPUs and many computers. The reason for training with very large datasets is that it is an easy way of reducing the error rates of deep learning systems. Very large datasets means datasets that are larger than the amount of storage you can easily fit into a single desktop machine or workstation. And once you cross that threshold, once your datasets are larger than that, you have to deal with distributed storage systems, with network communications, and many other issues. Even if you have smaller models, the techniques that make large-scale training work can still help you improve your training and workflows on those smaller models. For example, you can use cheaper rotational drives in place of expensive NVMe drives. You can achieve better reusability of datasets and processing pipelines because the big data techniques actually result in a more standard and more uniform representation of datasets. You can run many jobs on small datasets efficiently, for example, for hyperparameter search. If you're in an academic setting, you may want to set up a deep learning lab where many students use the same datasets for training. And again, these techniques help with that. And by standardizing how datasets are represented and how they are accessed, it's easier to exchange datasets with other researchers. Here you see a typical setup for a large-scale training job. In this case, you see a 4-node, 4 GPU per node setup. Usually you would actually have many more nodes than just 4 nodes, but this is just for the purposes of illustration. And I should say that by node, I mean server or computer or machine. Now, when you train models on multiple nodes, network communications becomes an issue. And there are two major forms of communication involved in multi-node training. First, nodes need to communicate among each other to synchronize their weights for distributed stochastic gradient descent. Second, all nodes need to receive training data from storage, and storage that is usually on distributed storage systems that are, again, only reachable over the network. Now, the first kind of communication, the weight synchronization, is actually well taken care of by existing libraries like TensorFlow, PyTorch, or Nickel. And in order to take advantage of those, is usually just a couple of lines of code you need to add to your PyTorch model, for example. It turns out that I/O is often the bottleneck and the hardest part of the system architecture for large-scale training jobs. And I/O is what we're going to be focusing on in the rest of this presentation. Now let's look at the typical path training data needs to travel in order to get from disk to the GPU in a multi-node training setup. So typically the data is read from disk on a storage node, then it's transferred over the PCI bus to memory, then transferred again over the PCI bus to a network card. The network card then sends it out over the network, where it may encounter switches and other network components, but eventually it reaches the network card on the GPU server. And then it travels over the PCI bus again, is transferred into memory, is usually processed and decoded by some CPU-based process, and then finally it's transferred again over the PCI bus to the GPU, and then the data is finally used in our deep learning model. Now, any one of these components can actually become the rate limiting factor. And the overall performance of the entire pipeline is determined by the bottleneck, by the least performant component. Some of these components are scalable. So for example, we can easily add more storage nodes or more GPU nodes if we want to. That's a question of money, but it's not a question of technology. However, the bus, memory, and CPU bandwidths on each node are limited by the PC architecture, meaning we can't just double the bus bandwidth by just paying more money for buses. The bus bandwidth is limited by what PCI buses on common CPUs can actually accomplish right now. Now, the optimal hardware utilization means keeping the most expensive components of the entire system utilized at 100%. So it's better to over-provision cheaper components of the system in order to keep the most expensive components, in this case the GPU, busy. So how much data does a GPU actually use? Well, the data rates at which typical high-end GPUs consume data for training with common models are between 200 megabytes per second and a gigabyte per second. And if you don't deliver data at that rate, the GPU will not be fully utilized. By the way, you can check the GPU utilization that you're currently having by using the NVIDIA SMI command. It will actually give you the GPU utilization in terms of percent, and that percentage should be upwards of 90% when you're using your GPUs efficiently. Now, many of you are probably already familiar with deep learning and have run something like a PyTorch or TensorFlow model on your desktop, and you haven't run into any of these limitations. And that's because most datasets used in deep learning for publications or experimentation are not all that large. So a dataset like ImageNet is about 150 gigabytes large, so that easily fits onto a single NVMe drive. And an NVMe drive has data transfer rates of about 3 gigabytes per second. So a single NVMe drive can easily keep 4 desktop GPUs busy. Let's see how this works out for larger training problems. Let's say we have a 100 terabyte data set, 16 GPUs, and some kind of image recognition model that requires 200 megabytes per GPU per second. So on an NVMe drive, in order to meet those requirements, we need 100 1 terabyte drives just to meet the 100 terabyte total data size. And at $350 per terabyte drive, this costs us $35,000 for the storage alone. But this actually meets total I/O bandwidth, since this gives a total of about 300 gigabytes per second. And of course, we have 100 terabytes of storage. Now, this isn't the total cost because you cannot actually put 101 terabyte drives, NVMe drives, into a single machine. So you need multiple nodes in order just to hold the drives. Let's look at how this works for rotational drives, rotational hard disk drives. So for rotational drives, you might buy 16 8 terabyte drives. They're $200 each for a total cost of $3,200. This gives you a total I/O bandwidth of 3.2 gigabytes per second, and it gives you a total of 128 terabytes storage. And furthermore, 16 drives is something you can fit into a single machine or maybe into 2 machines. So the cost of rotational drives to meet the requirements for this fairly typical large training job is much lower than for NVMe drives. However, in order to be able to use rotational drives, we have to use some special techniques. And in order to use distributed drives or distributed storage, we also have to use some special techniques. And that's what we're going to be talking about next. So we probably need rotational drives, and we probably need multiple nodes and network transfers. How can we achieve good performance? There are really 3 key principles for making this kind of architecture work efficiently. First, we need to use sequential I/O. Second, we need to use pipelining. And third, we need to use sharding. We will look at these in turn over the next few slides. Let's first look at how regular PyTorch and TensorFlow training works. Let's consider a problem like ImageNet training, a problem where we have 1 million images, and let's say these images are stored under some base directory. Now, file-based dataset representations in PyTorch allow us to access training samples in any order we choose. And we usually choose to access samples in random order because that's beneficial for the kinds of optimization algorithms we use in deep learning. So for training, we pick a random index, we then retrieve the training sample corresponding to that index, and finally we train on that sample. That's illustrated by the pseudocode there. Now, retrieval of the training sample involves loading the corresponding image file from disk, and this translates into random access to disk. So for each image, for each index that we choose, we make a random access to disk. We move the disk head to some other location on the disk, load the image, and then move it again. This usually gets data rates of about 20 megabytes per second. For sequential I/O, we take all the training samples and put them together in a single file. We can do that, for example, by simply creating a tar archive of all the image files in the training set. Now, when we read the images from that single data file, those reads are purely sequential. And in Python, we access such a data source using iterators and using the Python next function. In fact, PyTorch has a special class for these kinds of datasets called iterable datasets. Using this kind of access pattern, we can now achieve 200 megabytes per second read speeds as opposed to the 20 megabytes per second for random access. Of course, we still need to shuffle the data. We can do that with an in-memory shuffle buffer, and the pseudocode illustrates a simple way of doing that. Now, this kind of in-memory shuffling gives us some degree of shuffling. It's not the same as fully random access, but it is good enough for deep learning. And furthermore, we can actually improve shuffling further by using a technique called sharding, which we will talk about later. So, the performance difference between random access and sequential access is substantial. For rotational drives, random access gives us about 20 megabytes per second read speeds, while sequential access gives us about 200 megabytes per second read speeds. Furthermore, sequential access also happens to work better for distributed storage and network access to storage. And this idea of using sequential access for speeding up big data operations actually has a long history. It's used in TensorFlow with TF-Record, TF-Example, and Google GFS. It's been the basis for Hadoop and MapReduce frameworks, and it goes all the way back to Fortran and mainframes from the 1960s, where the primary storage medium, the primary large-scale storage medium, was tape storage, which is intrinsically highly sequential. Now, closely related to the idea of sequential access is the idea of pipelining. By making all access sequential, we actually get pipeline efficiency very easily. Let's see what this means. So consider a network storage server. On the left-hand side, you see usual access patterns between a client, green, and a server, yellow. If you attempt to run a file-based dataset implementation against a network storage server, you usually get these kinds of access patterns. That is, the client picks a file to read, sends the request to the storage server, and gets back the data for that file. Overall, this results in a lot of back and forth between the client and the server, and a lot of waiting between the client and the server for requests and responses. Now, on the right-hand side, you see what happens with sequential storage. With sequential storage, you make a single request, and in response, many training samples flow from the server to the client. And this results in much higher throughput. You can actually see this even in this simple diagram. Now, you can certainly bundle many random access requests to the server and attempt to execute them in parallel and asynchronously. So in principle, you can take the left diagram and issue the requests from the client to the server in parallel, and then wait for the responses in parallel as well. However, this is more complex and actually no better in practice than simply moving to large sequential storage representations. So another idea that is worth discussing briefly is caching. Since we know that random access to the local NVMe drives is fast, why don't we just use a regular network file system and use the local NVMe drive as a cache? But keep in mind that for deep learning, we make repeated iterations through the entire training set. So if the training set is much larger than the local NVMe cache, caching doesn't actually help, because after each iteration, any data we've cached will largely have been evicted already. Now let's look at the notion of sharding. Let's go back to our 100 terabyte dataset example. We could certainly store our entire dataset in a single 100 terabyte file and then access it sequentially. This is certainly efficient for reading the dataset. It gives us 200 megabytes per second I/O from a single rotational drive. However, that's all it gives us. It forces all processing and all reading to be sequential, and this is actually not a good choice. What we do instead is something called sharding. So with sharding, we take our 100 terabyte data set and we split it up into, for example, 10,000 shards of 10 gigabytes each. Now, this lets us do two things. First of all, it lets us access shards randomly. So if we want to read data in random order, we first permute the shards. So we read the shards in random order, and then we read each shard sequentially and use an in-memory buffer for shuffling. But the other thing we can also do now is we can aggregate bandwidth across shards. So this slide illustrates this idea of sharding with an example. In a simple illustration, we have 5 rotational drives, 5 storage servers, and we store 2 shards per storage server. The left-hand diagram shows how we can use the setup for achieving high I/O rates to feed data to a GPU using parallel I/O. What we do is that we arrange for each storage server to pick one shard to read, and to read that shard sequentially, and then send the training data from that shard over the network to the GPU. Since each disk drive delivers data at 200 megabytes per second when we read sequentially, the aggregate bandwidth and parallel I/O is 1 gigabyte per second in this example. Now, in order to make this work, it's important that we only read one shard per rotational drive. If we start to read 2 shards, we don't actually get half the bandwidth for each shard. We actually get a substantial performance degradation. Using storage servers like AIStore, we can actually scale this up to many, many more drives than just 5 drives. So for example, if you have 1,000 drives, you get 200 gigabytes per second of aggregate I/O bandwidth out of AIStore. And storage servers like AIStore ensure that each shard is read from one disk, and that each disk is only used efficiently to read one shard at a time. Now, the right-hand diagram illustrates how to use this setup for parallel data processing, for example, like format conversions or data augmentation. So let's say that each shard contains 5,000 PNG images, and we want to convert those PNG images to JPEG format. We first write a conversion job that sequentially steps through an input shard, performs the conversion from PNG to JPEG for each image, and then sequentially writes an output shard. In a MapReduce setting, that is basically the map phase. Now, we can do this in parallel now for each available input disk drive without it affecting read performance. So we can, since we have 10 shards stored on 5 drives, we can read from 5 shards in parallel, process those shards, and then write out the result again as a sequential file format. So we get 5-fold parallel processing. And again, this is very similar to the kind of parallel processing we get in MapReduce jobs. And the degree of parallelism that's achievable is usually not determined by CPU limits, but by the available I/O bandwidth. The distributed system we've talked about so far is a 2-tier architecture. There is the storage tier and the deep learning tier. If we zoom into a single GPU node in such an architecture, we can see that it actually performs several functions. So it receives data from the storage system, and then it decompresses and augments the data, and finally transfers it to the GPU for training. Now, all that processing is usually handled by the CPUs on the GPU node. So in TensorFlow, this processing is carried out by threads deep inside TensorFlow. In PyTorch, it's carried out by worker processes, with the number of workers given by the numWorkers argument to the data loader class. And in the diagram, you see these workers indicated by the small blue rectangles. Now, the number of CPU cores available on a GPU node is strictly limited. So in these kinds of architectures, there's a limited amount of pre-processing that we can perform. Now, in some cases, moving the pre-processing to the GPU can help. DALI is an NVIDIA library that does this. But this also takes away resources on the GPU and limits the kind of deep learning models that we can train. So a different solution would be nice to have. The use of sequential I/O actually allows us to easily remove the bottlenecks that we saw with the 2-tier architectures by moving to a 3-tier architecture. So in such an architecture, the data from the storage server is first sent to a collection of CPU nodes or servers that perform decoding and data augmentation, and then those servers send the training batches to the GPU servers for the actual training. Now, this may sound complex, but it's actually pretty easy to implement once you have sequential I/O as the basis of all your training and data representation. So another reason for using such a 3-tier architecture is that the data transfer from the CPU nodes to the GPU nodes can be RDMA-based. And that's important because RDMA-based transfers can avoid the PCI bus, the main processor's PCI bus, entirely. And we need this for GPU servers that have large numbers of GPUs. For example, DGX2 has 16 GPUs. If we weren't using RDMA, the PCI bus would become a bottleneck in such a setup. Now, notice also that the middle tier in this 3-tiered architecture can actually also use GPUs and can use tools like DALI. You can configure and deploy such 3-tier architectures using platforms like Kubernetes, and that's actually pretty simple. However, a 2-tier architecture is still easier for end users. So in many cases, it turns out that we can combine the scalability of a 3-tier architecture with the convenience of a 2-tier architecture by incorporating the middle tier into the storage system. This is what the NVIDIA AIStore server accomplishes. AIStore is an open source project, and you can actually just download it from GitHub. AIStore provides efficient sequential storage, and in addition also permits functionality like data augmentation and format conversions to be carried out transparently. So from a deep learning developer's point of view, AIStore looks like a simple storage server, but internally can take care of the scheduling and execution of many middle-tier functions. So that has been a quick overview of the structure of very large-scale deep learning jobs. Now, how can you put this into practice? TensorFlow has some built-in support for these kinds of large-scale training jobs. For distributed storage, for example, it supports the Hadoop file system and cloud storage. As its sequential data format, it uses TF-record and TF-example. And this kind of I/O is also supported through the TF-data and TF-IO libraries. And there are equivalent libraries for PyTorch as well. However, these libraries and representations are not ideal for deep learning because they were originally developed for big data applications. So HDFS can actually be pretty tricky to install and configure. And formats like TF-record are designed for serialized data structures. But many of the data structures we use in deep learning are simple compressed audio and video data files. So what we're actually going to use in the next few presentations, where I'm going to show you how to put this into practice, is a new library called WebDataSet. WebDataSet actually stores training data simply as tar archives. So it's a faithful and bit-identical representation of data the same way it is stored on disk. And furthermore, it also uses HTTP for its distributed storage protocol. So unlike HDFS, you can actually use any web server for serving training data to deep learning jobs. Of course, all of this also works very well for local files, and you get the benefits of a sequential storage format when you use WebDataSet on local files. So, in summary, I/O is often the primary bottleneck for large deep learning jobs. And we've seen a number of ways in which we can overcome this bottleneck. The two most important principles are the use of sequential storage formats and sharding. And we can also combine that with 3-tier architectures to achieve scalability for pre-processing and data augmentation. So as I was saying, in the next few presentations, we're actually going to look at how this works in practice. Thank you.